Hello everyone and welcome to the next instalment of Amicus Recruitment's Python live webinars, powered by the live series itself. Now, for those of you who don't know who Amicus are, we are an IT recruitment agency that operate across the UK, throughout Europe and the US as well, and solely specialise in recruiting across three key areas of IT, which include Python, Golang and JavaScript. Now, my name is Jordan Hayward and I will be your host today, and I'm joined by the fantastic Niels Bantilan. I hope I pronounced your last name right there, Niels. Apologies if I haven't. But Niels is a machine learning expert and open source fanatic who has put together a brilliant workshop today focused around data quality and data testing with a brand new open source tool, Pandera. So the talk will be interactive as per usual, and there will be a Q&A tab at the bottom of your screen. So if you do have any questions throughout, please chuck them in there and myself and Niels will navigate through them during the course of the workshop. But yeah, quick introduction done. That's enough from me. I'm going to hand over to the man himself. So welcome, Neil. Thanks for joining us today.
Awesome. Thank you, Jordan. I guess I prefer open source zealot myself, but fanatic would be accurate.
Yeah.
Let me share my screen. If thumbs up if you can see that.
Yeah.
Hopefully you can.
I can see it. All good.
Perfect. So yeah, today I'm going to spend maybe 45 minutes talking about statistical types for pandas, DataFrames, and friends. Basically, what you'll get out of this is you'll get a better understanding of how to parse, validate, and synthesize data frames with generative schemas. Before jumping in, a little background about myself. I did my bachelor's undergrad in biology and dance. I got a master's in public health, focusing on the behavioral social science aspects of it, and also public health informatics. These days, I'm the chief ML engineer at Union AI, a startup that is building the infrastructure fabric that is aiming to unify data and machine learning into a single platform. I'm also an open source maintainer of the FlightKit flight package, the author and maintainer of Pandera. I've also written another package called UnionML. And so if it's not obvious, my mission in life these days is to make data science and machine learning practitioners more productive. So with that out of the way, I wanted to dive into the outline of this talk. You might have seen it in the promotion posts on LinkedIn and whatnot, but just to go over it here, I first want to motivate this talk with a section on why I should validate data in the first place. I'm going to go into data testing and how I can put it into practice, obviously defining these terms. I'm then going to go into Pandera quickstart, Pandera being a data validation package in Python for validating pandas data frames and pandas-like DataFrame-like objects. I'll define what statistical types are. So if any of this terminology is unclear by the end, hopefully you can ask questions. I'll go into two examples on using Pandera to validate a data analysis pipeline and a machine learning pipeline. And then finally, tie it all together with a conclusion on how you can start using Pandera in your own work. A little preamble here before I dive in is you can find the slides at this link here. We'll probably share this maybe in the chat or afterwards. And all the code is in this Jupyter notebook. So with that out of the way, let's get into it. Why should I validate data? So first of all, I want to introduce DataFrames. And for people who are not in Python or Pandas land, maybe don't program too much in Python or R, don't know what DataFrames are, you can basically think of them as tables, say Google Sheets or Excel, tables that you manipulate on a interface. But the difference with data frames is you manipulate them programmatically. So here's just a simple example of a data frame where each row is a person or attributes about a person, and each column is, let's say, the hours they worked for that week and then their wages per hour. So with that out of the way, data validation, to give you a high-level definition, is the act of falsifying data against explicit assumptions for some downstream purpose, like analysis, modeling, visualization. And so if I take this statement, this, say, a hypothesis about swans, and say all swans are white, one way of verifying this claim is to go out into the world and find swans and say, find all instances of them and confirm that they are all white. But another way to reframe this, you can think of this as basically the scientific method, is you can go out and find the one instance of, say, a black swan or a non-white swan. And now your hypothesis is falsified. You might have to go back and refine that hypothesis, add some conditional statements to it to make it more refined. So this is basically the scientific method, and it's very closely tied with data validation. So just to motivate this, why would I need it? Why do you need it? From a developer perspective, it can be difficult to reason about and debug data processing pipelines, especially when they get very complex. And it's also critical to ensuring data quality in many contexts, especially in when the end product informs some kind of business decision, scientific finding, or it generates prediction in a production setting. And this I want to emphasize very clearly, in that a lot of people start caring about data quality when you have, say, a software pipeline that's in production, that's not really, that doesn't have a human in the loop. But even in simpler settings where there's an analysis, right, you kind of want to validate your data, especially if the conclusions that you're drawing from your analysis inform some kind of critical piece, as I said here, scientific finding. And so to drive this point home, I want to make the statement that everyone has a personal relationship with their data frames or tables, So you might know the ins and outs of it, but maybe if you're in the team, or if you in the future might forget some of the details of what's in there, I kind of want to go through this story. And you can put yourself in the shoes that, imagine you're a data scientist maintaining an existing data processing pipeline. And one day you see there's an error, and you follow the error log and you see that there's this error that says, okay, I can't multiply a sequence by this type float. It's like, okay, that's weird. You find the function that's responsible for this error, and you look around and see that, okay, trying to compute the weekly income from hours worked and wages per hour. Pretty simple multiplication there. And so, I insert a breakpoint in the code so that I can go into like a Python runtime and inspect the data frame here called df. So I print it out. I look at the data types and I see, oh, weird. Okay, hours worked. I expect that to be some kind of number, but here it says object. And then I print out the types of each value in the hours worked column. And oh, okay, I see this value. It looks like a number, but it's actually a string. So this might be familiar to many of you who've worked in Python, worked with pandas, where, since Python is dynamically typed, things could have different types, unexpected types, just based on some kind of data corruption that you're not aware of. So, as a developer here, you squash the bug. You basically add some type enforcements here. So make sure that each column is of the expected type. You do the hours worked. You replace negative numbers, say, with null values. so hours work can't be negative. And then you do your weekly income computation. Okay, great. This, someone's going to handle these null values at some point down the line, so you don't have to worry about it. But a few months later, you come back and you find yourself at a familiar function. You might have just been looking, at the code base, and you see this thing, right? You see process data, but now it has this decorator, Pandera.checkTypes, and it has these data annotations on the input data frame, and you see this output annotation on the of the output of this function called process data. Okay, cool. So what's happening here? I've removed the line in back here that actually coerced the types of the data frame to your expected types. So what's going on here? So you look above your process data function, and you see these two schemas. And what these two schemas represent, I'll go into this later, but this is actual Pandera code, is I've defined through the syntax a way of enforcing the types of the columns of the data frames by saying, okay, hours worked is a float, wage per hour is a float. I want to coerce these types whenever I'm annotating the input or output values of the function that I'm decorating. So here, before DataFrame is fed into the process data function, it's going to be coerced into the correct types, and I'm going to do a bunch of checks on them to make sure that there are no I'm actually going to say here that the null values are allowed, so there are no additional checks here. But with process data, I'm basically inheriting from raw data. So if you're familiar with Python inheritance, I'm inheriting from raw data, and I'm attaching additional properties to hours worked, namely that the values must be greater or equal to 0. So the moral of this story is basically, the better you can reason about the contents of the data frame, the faster you can debug. In that previous slide, you saw that I'm explicitly encoding the assumptions about the inputs and outputs of the contents of the data frame in this fictional story. But the point here is that the faster that you can debug, the sooner you can focus on downstream tasks you care about. And by validating data through explicit contracts, or schemas as I'll call them, you can also create data documentation for the rest of your team or for yourself in the future when you've forgotten what the properties are. So hopefully I've motivated why data validation is useful and a good practice. But now I want to go into data testing, which is a related concept. And I want to describe to you how you can put it into practice. So just as a reminder, data validation is this act, right, of falsifying data against your assumptions about that data. And it's always grounded in towards some kind of goal, be it an analysis, model or visualization. Now, to extend this idea, data testing is this idea that you're validating not only real data that's coming in production, but also the functions that produce them. So what does this mean? In the real world, you'll have some raw data. You have really no control over how, often you'll have no control over how that data comes about, how it's generated, how it's collected. So you want a way of creating some kind of boundary in this raw schema box here that says, okay, these are at the very least, this is what the raw data should contain. Maybe you specify types, maybe you don't, but you at least have a baseline of, okay, these are the columns that my table should contain. When you apply the transform function to that raw data and you create some kind of transform data and you feed that downstream to some analysis, you also then want to have these basically guardrails for what is the output of this transform function? What does that look like? And typically this will look a little more strict. So maybe, as you saw in the previous slides, and I'll dig into later, this transform schema tends to be more strict. So you're kind of adding more assumptions. You're saying what the transform function should do to clean up the raw data. So that's one aspect of data testing. The other side of data testing is in your test suite. So, I've created this transform function and it's supposed to clean up my data, but how do I actually know that in a non-production setting? So when you're developing this transform function, you want to be able to give it test cases, which are oftentimes hand created. So you create the data frame, or you create those inputs to the transform function, usually in your unit tests, and then you get a transform data, data frame out, and then you make some assertions about that transform data. In this setting, I'm hinting at some of the features that Pandera gives you, which is that if you recall, I'm talking about generative schemas here. Pandera schemas can actually be used to generate test cases. And then you can use downstream schemas to then validate properties about the transform function, thereby testing the functions that produced this data right here. So data testing in practice is the iterative process. So you first define a goal, but then you iteratively build domain knowledge about the data at hand with respect to that stated goal. You then, in parallel, this kind of harkens back to test-driven development. You implement maybe your tests first, and then you implement the functions that implement the actual functionality. In parallel, you verify the data, and if your checks pass, you continue your analysis. So this has all been sort of in the abstract so far, and so now I want to dig into the meat of things with more concrete code implementations and examples. But for now, I just wanted to take a pause. Jordan, if there's any questions, be happy to address them here.
At the moment, no. I've been keeping an eye on it. I think a great introduction to Pandera, but no questions at the moment. But I will keep my eye on it moving forward.
Awesome. Okay. Great. So moving forward, in the next part, I'll give you a little tour of what it looks like, how you would use it in practice. There are a lot of features at this point of Pandera. I've been working on it for almost 4 years now, but these are the main core features that I want to highlight. So Pandera is an expressive and lightweight statistical typing tool for data frame-like containers. So you can check the types and properties of data frames, easily integrate them into your existing data pipelines, and synthesize data, as I was mentioning earlier, for property-based testing. And if you're not familiar with property-based testing, I'll show you like a kind of an example of it, and now you have a Googleable term if you're interested in learning more. So Pandera comes in 2 flavors. This is the original flavor, the object-based API. And this was very much designed to look and feel like how it is to define a pandas data frame. So you define a data frame schema. First of all, you import Pandera, but you define a data frame schema and you say what columns it contains with the keys for the names of the columns. And the values are basically these column objects that have where you state the properties of each column. So this column is a float, must be greater or equal to 0, and it can contain null values. Categorical is a string, and it must be within this finite set of values ABC, and it's also nullable. By providing the course equals true option, I'm saying that whenever I call the data frame, the clean data schema, so clean data schema dot validate some raw data, I'm going to first coerce all the columns into these types before applying the rest of the checks. So that's all that means. There's a second newer flavor of Pandera, which is designed after Pydantic, if you're familiar with that, or data classes, which is in the standard Python library. And the class-based schema looks very much like the object-based API, but here you inherit from this schema model base class, and then these class attributes are then how you define the columns and their types. Here, additional properties about them. This config class within the schema model is how you define, DataFrame level configurations, like over here. So again, this is the main reason. So Pandera is one of those projects that was, scratching my own itch, and that itch really was knowing, I wanted to know where exactly an error occurred in the data frame I was working with. So here I've introduced 2 negative values in the continuous column, and then 2 invalid values in the categorical Z and X. And when I call clean data.validate with lazy equals true, I'll unpack that in a bit, but when I call this schema.validate method, I can catch the schema errors exception. So if the data is valid, it'll just return the valid data with the coerced columns. But if there is some kind of issue with the data, a schema errors exception is raised, and it exposes this failure cases attribute, which is itself a pandas data frame, and it contains very granular information about what went wrong. It says what the failure case was, what the check was that was checking for that failure case, which column that occurred in, and which context. So in this case, the column. It gives you the index also of the original data frame where that error occurred. So this is really the main workhorse, like the main core feature of Pandera. Another really nice thing that Pandera offers here is that you can transform your schemas via method calls or inheritance. So with the object-based API, I've defined this raw data schema, which is just, it just outlines what the types are, or what the column names are and the types. But then you can, dynamically on the fly update them and, attach additional attributes about them. So say I want, clean data schema to have nullable columns for the continuous column. And then I want to add a check to the categorical column here. What this looks like for the class-based API is very similar. There are kind of trade-offs between the 2 styles. But basically, I'm inheriting, so I'm defining this raw data schema with the schema model. It looks like, what I showed you before. And now I can inherit from the raw data schema and define this clean data schema. Note that I'm not actually updating the types here. I'm just updating the properties that I want to check against for the clean data. And therefore, I'm like, you can see here, if there's a function that uses raw data as input and clean data as output, you can kind of infer what that function is supposed to do. Cool. So now you define schemas, it gives you errors, you can update them. How do I actually use it? So this is a perfect example of how you can integrate it seamlessly with your existing code. So say you have a function fn. It does everything we need to do for our raw data to be transformed into clean data, namely that it's just converting negative values to null values here in the continuous column. And then in the categorical column, it's converting values outside of the distribution A, B, C into null values as well. By adding this check types decorator, I'm making sure that I'm doing runtime checks on the raw data before it's fed into this function. And then after this function has done its computation, it's returning the data frame. that clean data schema is being applied to that output. Cool. So this is really like the three pieces to get started with Pandera. The next feature that I think is very cool that I want to share with you is generative schemas. I've mentioned this before, but with the clean data schema, I can call the .example method here, and I can say what size data frame I want to create, and it'll generate a valid data frame under the constraints of that schema. So, it's generating all the same data, but depending, it's kind of a random sample, or it's randomly generated. So every time you call .example, it will generate a different set of data for you. You can use this in data testing, right? So when I said data testing was validating real data, but also the functions that produce the data, I'm testing the function, the fn function that I just showed before in this unit test. And let me just unpack this a little bit. So I'm using this library called Hypothesis. It's a fantastic library. It has a lot of stuff in it as well. So that's probably a topic for another talk. But I can basically use this given decorator. And if I say given a raw data strategy, which is a strategy for synthesizing data of size 5, basically the input of this function becomes raw data, basically a generated data frame that I can then feed into function. And because function, again, has this check types decorator, it's going to check both the raw data and also the output of function. And so, if you're familiar with unit testing and like PyTest and packages like that, you generally have to do a bunch of assertions after this, right? But with Pandera, basically your unit test becomes an execution test. So you execute raw function, and it'll validate everything for you. So the next thing here is, okay, so pandas is great if your data fits in memory. But what if it's a large, very, very large data set? How do I scale it? So pandas friends would be Dask, Modin, and PySpark pandas. These are all almost drop-in replacements for pandas data frames, but they allow you to scale to out-of-memory data structures. So here I'm just displaying some raw data that I'm going to play around with to show this example. This is the same raw data that I've showed you in the previous slides. You can apply a single schema, this clean data schema that we at this point know and love. But to Dask data frames, the code looks the same for Modin data frames, and the same goes for PySpark pandas data frames. So it'll give you the same errors. It's effectively the same set of features and validation rules, but now I'm able to use these other data frame-like objects. And so this concludes the Pandera quick start. Hopefully that gave you a flavor of all the things that you can do with Pandera. As a meta comment here, just to pause, basically all the code that I'm showing you is validated by Pandera. So this presentation is written in Jupyter Notebooks. You can see here, I'm actually running the tests. So I'm actually running these code snippets, and it's printing out that these tests have passed. And even with the cases where there are errors, right, I'm catching those errors and I'm showing them to you. So this gives you a pretty good idea that, of how powerful Pandera can be, both in a production setting where, you have a system kind of running on its own, or, a notebook setting where you're doing an analysis where it actually might be useful for you to validate all the visualizations and analyses that you have in the notebook. So before actually, I want to go to the examples, but I want to quickly go into this idea of statistical typing. I mentioned it earlier, and when I define it, it'll be very clear to you. But first, I want to motivate type systems more broadly, right? So type systems help programmers reason about and write more robust code. And actually, type systems also help machines reason about and compile code, not in Python, but in other languages. But in Python, the type system since, 3.6, allows you to annotate your functions and your methods with type annotations. And it gives you a way, combined with tools like MyPy, it actually gives you type linting, but it gives you a way of documenting, what are the expected input and output types of your functions. So, just to somewhat not strictly prove, how this can help you reason about code, right? If I have this function add and double, and it takes two numbers, x and y, and it outputs a number, even without the implementation of the actual function, you can sort of guess, which one of these function calls are not like the other. You can kind of tell, okay, this is an invalid function invocation because I'm giving it a string instead of, integers and floats. And similarly, with all the Pandera code you've seen so far, you can see an equivalent in DataFrames, right? So I have a raw data frame. It has an X and a Y column, both integers. And I want this add and double function to output another data frame that has a Z column. And I'm defining a custom check here on the fly as a method to this output schema. And, this is kind of wasteful because I'm doing the computation all over again, but I'm adding X and Y together and I'm doubling it. And I'm making sure this right-hand side equals the left-hand side. So this is an equivalent way of saying, okay, here are my two data frame inputs and outputs to this function. And this is a way of encoding the assumptions about what this function does. In this case, add and double X and Y. So statistical typing, in very brief terms, is a system that extends primitive data types like ints, floats, strings, with additional semantics about the properties held by a collection of data points. So what does this mean? If you consider a single data point, say you have a dictionary of square footage, number of bedrooms, price, the unit of analysis here is a house. What can we say about these things? So you can say what the primitive data types are of each of these fields are. You can maybe state what the value ranges are for each of these using your domain knowledge, allowable values. For strings, you can do some kind of regex string matching. You can say if a field can be nullable or not. But now consider a collection of data points. So now what you can do is, the first thing you can do is apply those atomic checks at scale. So if you have some kind of framework like pandas, they have vectorized implementations of various atomic checks that you can apply very quickly. However, there are things that you can check with a collection of data points that you can't with a single one, right? So hence statistical typing, is that you can check for uniqueness across the square footage column, right? Or some ID column. You can check for monotonicity. Is the value of something always increasing or decreasing? You can check the properties of standard descriptive statistics. And you can also do fractional checks. Say, I want to check that 90% of my data points are not null. So you can do these things with statistics, right? Hence the idea of statistical typing. So Pandera is really a statistical type system geared towards data science and modeling, right? So it's defined with multiple layers. First you can define the primitive data types of the columns or fields in your collection of data points. You can state what the deterministic properties are. So these are things that you hard code. Say this has to be greater or equal to 0. And you can also state what the probabilistic properties are. So these would be properties like distributions that apply to the variable and their sufficient statistics. So you could do checks over the mean, or you can even say, is this collection of data points normally distributed, for example. So in the last two sections, of this talk, I'll go through these fairly quickly since I've given you a lot already of ideas to chew on. I just want to give you an example, two of them, for data analysis and machine learning, and how you could use Pandera to validate them. So in this case, we'll use the California housing data set. This ships with sklearn out of the box. And if you can see that there are like attributes about housing districts. So these are actually aggregate. Each row is a housing is a district in California, and each column is some aggregate attribute about the houses in that district. So even with a cursory glance at this data, you can already tell what the types are, what the ranges are. So I've gone ahead and created a Pandera schema for the housing data, right? So each of these median income of the district, latitude, longitude, and then the target variable for most machine learning tasks is to predict the median house value. And I've slapped on various plausible ranges for each of these columns. Using this schema, I can create a read data function, that always validates the output of this fetch California housing function. And now I have this housing data frame that I can start playing around with. So in my analysis pipeline, I want to test this hypothesis that median income is positively correlated with median house value. So how would I do that? This is a code snippet that would do this using pandas, and I'm creating, outputting the Pearson correlation coefficient, so positive numbers are good, and I'm plotting it out so that you can visually see that they are positively correlated. So you can bake in statistical hypothesis testing into your pipeline by, say this is a hypothesis I want to encode as a custom check. Pandera allows you to create these check extensions with this register check method. And what this does is it checks if two variables in a data frame are positively correlated using the SciPy Pearson R function. Won't get into this too much, but the test passes if the R correlation coefficient is greater than 0 and your p-value is less than some predefined alpha value. So I can dynamically create schemas here in my analyzed data that uses this check in my housing data hypothesis schema. So I'm saying variable 1, variable 2 are positively correlated with some alpha value of 1%. And I wrap this all into my analyzed data function so that this hypothesis is actually programmatically checked every time I run this function. So, I wrap this thing all into analysis pipeline. I read the data, I analyze it with that function I just defined. And every time I call it, I am guaranteed that I'm going to run this hypothesis test every single time. You could, of course, hand code this, right? So you could put this code snippet within the analyzed data function, but by defining it in the schema, it then becomes this reusable artifact that you can reuse across, your Python modules and your unit test suite, etc. The final example I want to show off here is a machine learning pipeline. So this will be a very simple pipeline, right? The prediction task is using all the features, predict the median house value of that district. This is a simple pipeline where I split the data into training and test splits. I then parse the data into features and targets. I train the model, just a linear regression model in this case, and I evaluate the model for this R-squared coefficient. So note here that all I'm doing here is I'm adding this check types decorator to just this split data function. And this highlights the fact that you don't have to validate everything, right? You as a practitioner can determine where in your pipeline is the most critical part to just make sure, okay, the data is as I expect at this critical point. Even though I'm using it in my parse data function, note that I'm not using check types here. So this is more of just a type annotation for humans, really. And at this point onward, I'm just using pandas.dataframe and pandas.series to annotate things, again, just for for humans reading it. So this is the pipeline. I can wrap it all into a run training pipeline function. Takes in the raw data, it splits it, parses it, trains the model, evaluates on the train and test split, and then it returns the model itself, as well as the train and test R-squared coefficient values. So here it is. It's I've called it in this notebook, and there have been no issues. So, great. Finally, here's an example of unit testing a training pipeline. So if you've ever pulled your hair out hand coding data frames or similar complex data structures just to test your pipeline, you can rest assured with Pandera, you can get rid of that entire step. And as I showed you earlier, I'm using hypothesis here, the hypothesis library, to basically generate 20 rows of housing data, again, under this schema, right? So it's going to produce all sorts of wild data that's actually not in the distribution of the actual data. But what this test allows you to do, what this test allows you to do is just make sure that your pipeline is running, like that the code executes, and that here I'm actually checking the predictions, right? So I'm checking the predictions of my model are mostly positive, even though the median house value is positive. Sometimes your model will find some kind of intercept where you'll actually get negative predictions. So you would have to iterate on your model to make it more robust against those cases. But this is just to show you that I'm doing a kind of a end-to-end pipeline test as a unit test just by synthesizing data using my schema and then using Pandera, after the fact to make assertions about the predictions that model produces. Great. So I've given you kind of this whirlwind, tour of Pandera, what it does. How can I start using it in my work, if you're asking yourself that question? So I'm just going to end with these couple of tips. So you're already encoding domain knowledge. So you're already building up domain knowledge while you explore your data, right? You're already plotting it, you're looking at it, you're already sort of becoming somewhat of an expert of that data. So why not encode it into schemas? Well, one reason is some data sets are very complex and they have a ton of columns, So if you're in a hurry, you can use Pandera.infer schema. Oops, I didn't mean to do that. Oh, cool. So that's the documentation. So if you access these slides later, you can go to this feature of Pandera. And what it actually does is it does a lightweight profiling of your data frame. And then you can then write that out to a Python script and iterate on it. So you can bootstrap a schema and refine it over time. The third thing is you don't have to write a schema for everything. You can identify the critical functions in your data processing pipeline, create a schema for those, and add a check types decorator as checkpoints for those key pieces. You can also, codify data quality checks that are specific to your problem domain, like that correlation check that I wrote earlier. And you can make it reusable by registering it with this register check method. And as I showed you time and again in this presentation, you can reuse schemas for multiple purposes, both for runtime validation and test time validation. And a final point here is once you've done all these things, you can be more confident in the correctness of your analysis or model with a schema that's both programmatically enforced and self-documenting. So you and your team can come around these schemas, look at them to see what assumptions need to be updated, what the assumptions are in the first place, and have a source of truth for what is flowing through your pipelines instead of just like a black box of just a data frame, and it can contain anything. The future roadmap for Pandera is to improve its extensibility. So there are a bunch of other data frame-like data science containers, I'll call them. Not all of them map easily to tables, but we want to support those. We want to improve the user experience with error reporting and more built-in checks, and interoperability with the rest of the Python ecosystem so that it's easier to integrate with your current workflow. And lastly, here's just a call to join the community if you're interested in this work, or if you want to be a user. Discord is a good place to ask questions. You can reach me at Cosmic B-Boy on Twitter, Niels at Union AI. The documentation is here, and yeah, I hope you learned something new today. And let me know if you have any questions here or offline. Thanks.
Perfect. Thanks for that, Neil. We do have a couple of questions that have come in. So I'll just read them out to you now. So the first one was, what if column names in raw data change? Will schema validation work, or will it be an error?
Yeah, for that question, so if they change, it'll be an error. So the short, that's the kind of the short answer. Because schemas are basically, they're stateless, right? You define them in code, and if it doesn't conform to those specifications, then Pandera will blow up. That said, there are ways of making it more flexible. So there's a way to define a regex pattern, right? That will match multiple different kinds of column names. So that's an option as well, if you want a little bit more dynamism in the way you're defining schemas. That I can post a link to the documentation here.
Perfect. And then the second question was, what motivated you to develop Pandera? Was there something missing from existing data validation libraries like Cerberus? Am I saying that right? Sorry.
Yeah, Cerberus.
Yeah.
Yeah. So when I built this out, to be honest, I just kind of wanted to do it for fun. And I wanted to the main motivation was, can I make something that's super intuitive to use for myself? Like having looked at options like Cerberus, actually Pandera initially was dependent on this library called Schema. It's still around and it's still super useful. But yeah, so really the motivation was I kind of wanted to try to design an API that was super intuitive for me to use. And then, how can it be so easy to use that it's like, you don't need any config, you don't need to really understand much besides, pandas, since this was a pandas first tool. It's obviously expanded in scope a little bit, but then that motivation sort of changed over time as people started to use it and feature requests started coming in. But to answer your question maybe more succinctly, the core of it was I wanted to define DataFrame schemas super quickly without a lot of the verbosity that I see in other similar packages.
Perfect. No, yeah, thank you so much for that. So that's the end of the questions. So yeah, thank you so much for that workshop, Neil. It's great to see individuals like yourself taking new tech to market, and I really appreciate you giving everyone an introduction to Pandera and what you're building at the moment. So thank you so much for your time today. I'd also like to thank everyone who attended, and thank you for the questions that came in. I hope you all, and I'm sure you probably have taken something away from the workshop today. And if you do have any questions afterwards, like Neil said, please do feel free to contact him. I'm sure he won't mind too much me saying that. So yeah, and if you enjoyed what you saw today and enjoyed this webinar, firstly, follow Niels on LinkedIn. He's always giving a talk on a webinar or at a local conference somewhere. So follow his activities on LinkedIn, and I'm sure you'll get a lot more information from him. And secondly, Amicus Recruitment and the live series are always hosting regular webinars across Python, Golang and JavaScript. So please do follow us on LinkedIn, subscribe to our YouTube channel as well, and you'll be notified that way. We do have another episode of Python Live next week, which will all be focused around computer vision. So Niels, feel free to sign up. Everyone that attended today as well, would be great to see you there as well. And yeah, I'm sure it'll be another great talk, just like Niels today. So again, Niels, thank you so much for your time. Thank you so much for introducing Pandera, and taking the time to put together a great presentation. And I'm sure I speak for everyone. We'd love to see you again on the webinar.
Awesome. Thanks so much, Jordan.
No worries at all. Thanks for a great speak, and yeah, speak to you soon. Cheers, everyone.
All right. Bye.
Bye. Bye.